Welcome back to the Deep Dive. Today, we're going beyond the basics of statistics to explore a powerful tool for understanding climate models, Bayesian Transport Maps. We'll be diving into a presentation by Professor Matthias Katzfus, who's at the forefront of this field. He presented Non-Gaussian emulation of climate models via Scalable Bayesian Transport Maps.
Right.
And we're going to unpack what that means for the future of climate science.
Professor Katzfus starts by reminding us that climate models, unlike weather forecasts, don't try to predict a single outcome. They aim to simulate the entire distribution of possible climate states. This is a computationally demanding task, and traditional methods often struggle to capture the complexity and nonlinearity of climate data.
So the challenge is representing the full range of potential climate scenarios,
Right.
not just a single best guess. And traditional statistical methods,
Yeah.
which often rely on assumptions of normal distributions, aren't always up to the task. This is where Bayesian transport maps come in. Could you give us a clearer sense of how they address these challenges?
It's helpful to start with a concept you're already familiar with, the inverse Cholesky factor. It transforms data from a general Gaussian distribution to a standard normal distribution. Transport maps extend this idea to non-Gaussian distributions. Imagine you have a complex data set with all sorts of peaks and valleys in its distribution. A transport map is like a mathematical function that smooths out those complexities, mapping it to a simpler reference distribution like a standard normal.
So instead of trying to wrangle this messy multidimensional data set directly, we're finding a way to represent it in a more manageable form. This reminds me of those maps that distort geographical size to represent data, like population density.
That's a good analogy. By mapping the complex distribution to a simpler one, we gain the ability to characterize and sample from the original data more easily. This is incredibly useful when dealing with the massive amounts of data generated by climate models. It's like having a key to unlock a treasure chest of information.
And the Bayesian aspect of this approach adds another layer of sophistication. Instead of defining a single fixed mapping function, we're working with probabilities.
Exactly. The Bayesian approach to transport maps involves placing priors on these mapping functions. Think of priors as our initial beliefs about the mapping, which we update as we learn from the data. We often use Gaussian process priors, which are very flexible and capable of capturing those complex nonlinear relationships we see in climate data.
So it's not just about finding a single best fit. It's about quantifying the uncertainty associated with that fit. And that uncertainty is crucial for understanding the limitations and potential biases in our models.
Precisely. The Bayesian framework allows us to incorporate and quantify that uncertainty, leading to more robust inferences and predictions.
Now, one of the biggest hurdles in climate modeling is dealing with the sheer volume of spatial data. We're talking about global models, which means managing data points across the entire planet. How do Bayesian transport maps handle this high-dimensional challenge?
Professor Katzfus addresses this head-on in his presentation. One technique involves specific spatial ordering schemes, such as the maximum-minimum distance ordering. Imagine you're placing points on a map. You start with one point, then select the next point furthest away. Then you choose the next point that maximizes its distance from those already selected. This creates a progressively denser grid over your spatial domain.
So instead of analyzing the entire global data set all at once, we're strategically breaking it down into a series of spatially organized prediction problems.
Yes, this spatial organization, combined with the fact that in many spatial processes, the influence of distant points decays rapidly, allows us to leverage sparsity. We can focus on a smaller set of nearest neighbors, significantly reducing the computational burden without losing essential information.
So it's a way of simplifying the problem without oversimplifying it.
Exactly. This is key to making these techniques computationally feasible for large-scale climate models.
But it's not just theory, right? These techniques are being applied to real-world climate model output.
Yes. Professor Katzfus shows how these methods have been used to model precipitation data. The samples generated from the learned transport map closely resemble the original climate model output, visually and statistically, even though they're based on a relatively small number of samples.
So it's not just a theoretical exercise. It's a tool that's proving to be effective in representing the intricacies of climate data. And this brings us to a really interesting point. Because climate models are about much more than just modeling a single variable like precipitation, we need to account for the complex interactions between multiple factors, such as precipitation, soil moisture, and runoff.
That's an important point, and Professor Katzfus delves into this in his presentation. He discusses how the transport map approach can be extended to a higher dimensional space, encompassing both physical and latent dimensions.
Could you elaborate on this concept of latent dimensions? How does that help us capture those interconnected relationships?
Think of latent dimensions as hidden connections between variables. Imagine we're looking at temperature and humidity. They're clearly related, but that relationship might not be directly observable in their physical spatial dimensions. Latent dimensions allow us to represent those unseen dependencies, giving us a more complete picture of how those variables interact.
So by incorporating these latent dimensions, we're essentially adding another layer of depth to our analysis. We're moving beyond simply modeling individual variables to understanding how they influence each other within a complex system. Professor Katzfus provides an example using runoff, demonstrating how we can predict it based on observations of precipitation and soil moisture using this multivariate approach. This kind of modeling has clear implications for managing water resources, especially as climate patterns shift.
Yes, it highlights the potential of these methods to go beyond simply describing climate patterns. By capturing these multivariate relationships, we can start to make more informed predictions about how those patterns might evolve under different scenarios.
And that brings us to another crucial aspect of climate modeling: understanding how spatial distributions respond to external factors. Factors like greenhouse gas emissions or changes in land use can have a significant impact on the climate system. How do Bayesian transport maps account for these external influences?
That's where the concept of learning conditional distributions comes in. Imagine having a map that updates itself as the landscape changes around it. Bayesian transport maps allow us to model how a spatial field like precipitation changes in response to external factors like emission scenarios. We're not just modeling the current state, but how that state might evolve under different conditions.
So we're moving from static maps to dynamic maps, capable of adapting to new information or changing conditions. This seems essential for making informed decisions about climate change mitigation and adaptation.
Absolutely. By learning these conditional distributions, we gain a more nuanced understanding of the potential impacts of different policy choices or environmental changes.
Now let's shift our focus to one of the biggest challenges in climate modeling: calibration. We need to ensure that our models accurately reflect real-world observations, which involves adjusting the model's parameters until its output aligns with what we see happening in the real world. But given the computational cost of running these complex models, calibration can be an extremely time-consuming process. How can Bayesian transport maps help streamline this crucial step?
This is where the idea of using Bayesian transport maps as surrogates for computationally expensive climate models comes into play. Think of them as efficient stand-ins for the full models. Instead of having to run the full model repeatedly during calibration, we can use the transport map as a faster, more agile representative.
So it's like having a streamlined version of the model that can be used for rapid prototyping and testing. This would allow researchers to explore a wider range of parameter combinations and potentially identify promising avenues for model improvement much faster.
Exactly. These surrogates can then be integrated into optimization algorithms to find the best model parameters that align the model output with observed climate data. Professor Katzfus even touches upon more advanced techniques like Bayesian optimization, which can further enhance the efficiency of this calibration process.
It seems like Bayesian transport maps offer a way to not just analyze climate model output, but to actually accelerate the development and refinement of the models themselves. This has the potential to significantly speed up the pace of climate research.
That's right. By streamlining the calibration process and making it more efficient, we can explore a wider range of climate scenarios, test different mitigation strategies, and ultimately gain a deeper understanding of how the climate system functions. This deeper understanding is what we need to make informed decisions about the future.
So as we've seen, Bayesian transport maps offer a powerful and flexible framework for working with the complex, high-dimensional, non-Gaussian distributions we encounter in climate modeling. From representing complex distributions to handling spatial data to streamlining model calibration, they're proving to be a valuable tool for climate scientists. What are your final thoughts on the potential of these methods?
What impresses me most is how Bayesian transport maps bridge rigorous statistical modeling and practical application. They address the challenges of high dimensionality and non-Gaussianity in a way that's computationally feasible. This is what makes them so valuable for real-world climate research.
It's exciting to consider the possibilities. This opens up, imagine, rapidly exploring various climate scenarios or efficiently calibrating models using these techniques. This has enormous potential to deepen our understanding and guide better decision-making in the face of climate change.
Precisely. As Professor Katzfus emphasizes, this is an active area of research. We can anticipate even more innovative applications of Bayesian transport maps in the years to come.
This deep dive has given us a glimpse into a powerful new approach to climate modeling. These techniques offer a path to greater accuracy, efficiency, and ultimately, a more informed response to the challenges of a changing climate. Until next time, keep exploring his bog.